All right, so let's talk about DLL hijacking on OS X. My name is Patrick Wardle. I've worked at a bunch of acronym places, including the NSA, which I always have to joke is the only US government agency that I actually think listens. You know, the rest don't really pay that much attention. So I work as the director of R&D at SYNAC. SYNAC does crowdsourced vulnerability discovery with vetted security researchers. Basically, anyone can sign up to find vulnerabilities in our customers' websites, mobile apps, network devices, IoT devices, and I'll let you in on a little not-so-secret because I don't see any of our customers here. Their security is really bad, so it's a bloodbath. We always pay out a ton of bugs, a ton of money to our researchers. So if you guys want to make some extra money, get paid to hack legally, check out synac.com. All right, so before diving in, since we are in Vegas, I think it's good to concisely define any possibly ambiguous terms. So in the context of this presentation, when I'm talking about implants, I'm talking about persistent malicious code. When I'm talking about hooking, I'm talking about intercepting function calls, installing a hook or a detour. A Trojan is a malicious program, something that pretends to be legitimate. Injection is all about getting code into a remote process. And then finally, a backdoor is code that provides undetected remote control of a computer. All right, so today's talk can be divided into pretty much 3 parts. We're going to start with a brief overview of DLL hijacking on Windows. The core of the talk is then going to be talking about dilib hijacking on OS X. We're going to look at the features in the loader and linker that allow us to realize this attack. We're then going to talk about how to find vulnerable applications that we can hijack. And then finally, we're going to actually walk through some hijack examples because there's some nuances to getting this all work. And then finally, we're going to end with some attacks and defenses. So first, let's briefly talk about DLL hijacking on Windows. The reason we talk about this first is because it's conceptually very similar to dilib hijacking on OS X. It's also well understood. And finally, there's real-life examples we can look at of DLL hijacking that illustrate the gravity of this kind of attack. So most of you are probably familiar with DLL hijacking on Windows. It basically starts with an application that specifies just a name to a DLL instead of a fully qualified path. This makes the application vulnerable. Why? Well, it turns out when only a name is provided, the Windows loader will look in various application directories before looking in the system directory. So this is conceptually how it all works. We have an application that says, hey, I have a dependency on blah.dll. The loader says, okay, you didn't give me a full path, so I'm going to look in several directories for this DLL. I'm going to start with the current working directory or the applications directory before then going and looking in the system directory. So what a malicious adversary or malware can do is plant a malicious DLL in that primary search directory, and then whenever that application is started, the loader will be tricked or coerced into using the malicious DLL. Now, there was a lot of hype around DLL hijacking, a lot of media when it was first publicly discovered in 2010. And this is because it was very useful for malicious adversaries and malware. So using DLL hijacking, you could do a variety of things. You could persist without touching the registry. All you'd have to do is plant a malicious DLL, and it would get loaded. You could also do load time process injection. So if an application, say a browser, was vulnerable to DLL hijacking, you could just plant a malicious DLL, and every time the browser would be started, your DLL will get loaded into the context of the browser. It was also used to bypass UAC. There's some applications on Windows that are auto-UAC'd, which means when they're executed, they are automatically elevated without having to put in a username and password. If these applications are vulnerable to a DLL hijack, again, an attacker can plant a malicious DLL and then execute these applications, and their DLL will also be auto-elevated into the context of that process. And then finally, there were some aspects where this could be used for remote infection, where if an attacker could get a user to load something off a remote web dav share, they could also get their malicious DLL loaded from that remote share as well. So here are some brief real-life examples of DLL hijacking. The first is persistence. There was a blog written by Mandiant. They talked about all these unrelated samples of malware they found that were all called fxsst.dll, that were all in C/Windows. They looked a little deeper into this, and they found out that explorer.exe was vulnerable to a DLL hijack attack. Basically, if you plant a DLL with that name in C Windows, every time Explorer starts, which is automatically when the computer reboots, your malicious DLL will get loaded. So this is a really great way to persist without having to modify the registry. The second example is Prevesk. Sysprep.exe is one of those auto-UAC'd applications, and it was vulnerable to a DLL hijacking. So here's some source code from some malware that actually was abusing this to bypass UAC. It would plant a malicious DLL and then programmatically start sysprep.exe, which would load the attacker's DLL into its auto UAC process. So where does DLL hijacking stand today? Well, Microsoft fairly rapidly responded. They patched a lot of their vulnerable applications by specifying the fully qualified path instead of the name. And they also set some registry keys that would help control the loader so it maybe wouldn't be coerced or tricked as much. I thought it was pretty much done and gone, but when I was working on these slides about 2 weeks ago, there was a security advisory released by Microsoft that they had to repatch one of their applications because it was still vulnerable to this DLL hijacking attack. So this shows the longevity and bodes well for an attacker if we can find a similar attack on OS X. So about 6 months ago, I was reading Stack Overflow because I do some programming at work, and this is how I code. I just go to Stack Overflow and see what other people do. And I found this quote by this guy named Mark B. So wherever Mark B is, whoever he is, I totally owe him a beer because he kind of piqued my interest and said that any OS that does dynamic library loading is theoretically vulnerable to DLL hijacking. So today, I want to talk about dylib hijacking on OS X. Now, first you might be thinking, why are attacks on Mac a big deal? Well, this is kind of an obvious statement, but Macs are pretty much everywhere. You look around a security conference, college campuses, R&D centers, board meetings, everyone uses Macs. And of course, we all know anytime a technology becomes more prevalent, attacks become more valuable and more destructive. All right, so the previous terms I defined were kind of funny. These ones are a little more serious, but equally important. So when I'm talking about Mach-O, this is the executable format that Apple uses. So Windows has PE files, Linux has ELF files, Macs have Mach-O. Dylibs are simply dynamic shared libraries. Again, Windows has DLLs, Linux has .sos, Macs have dylibs. And then finally, load commands. Load commands are embedded in these Mach-O binaries, and as their name suggests, they are commands to the loader. So they do things like specify the memory layout, the initial execution thread of the main execution state of the main thread. And then for the context of this presentation, it's very important because they specify dependencies on dylibs that the loader should load. Now, since these load commands play such a pivotal role, I wanted to talk about them a little more in depth. So as I mentioned, they're embedded within the binary, and they're read by the loader when the loader is loading the binary into memory. And you can view them with tools such as Mach-O view or OTool. One of the most important load commands for this presentation is the lc load dylib load command. Basically, there's one for each dylib that an application has a dependency for. So this is kind of like an entry in the IAT on Windows. Basically, it tells the loader, hey, I have a dependency. Please go find that dylib and load it into memory. So let's take a closer look at this dylib, this load command. So it starts with the standard load command header, which just has the command number and the command size because it can be variable in length, and then has a dylib structure. This dylib structure has a name, which is usually a full path, and then some versioning information. Now, there's another important load command called the lcid dylib load command. And this actually shares the exact same format as the lc load dylib load command. And the reason why is it's because it's complementary. So applications have the lc load dylib load command, which tells the loader they have a dependency. And what the loader does is it goes and finds that dylib, and then in the dylib, it looks for the dylib's lcid load command and makes sure they just match. So that's why they have the same format. They're basically complementary. All right, so back to dylib hijacking. Let's specify exactly what we're trying to do. We want to be able to plant or drop a malicious dylib and then have it be automatically loaded by a vulnerable application. Now, let's put some constraints on this. So obviously, you could achieve this by patching a binary, putting in a new dependency, but this is going to break the digital signature, makes it pretty easy to detect. We also are going to say no other modifications to the operating system. So no modification of auto-run pless files, anything like this. Again, just plant a file on the file system. That's all we're allowed to do. Again, we also want it to be independent or global of the user's environment. So we're not going to modify any path variables or environment variables. If we could find such an attack on OS X that is simply dropping a dylib and getting it loaded by vulnerable applications, it would be quite powerful. And we'd be able to abuse it for attacks that were similar to DLL hijacking on Windows. So we could gain persistence, load time process injection, bypass security products, and maybe even open some avenues to facilitate remote infection. So on Windows, DLL hijacking was all about abusing logic in the loader. So let's start by looking at OS X's dynamic loader and linker, which is called DYLD. Basically, when an application starts, the loader does a few things. And these are similar to what loaders on other operating systems do. they're going to parse the application they're loading, look for the dependencies, go and find those dependencies on disk, load them into memory, and then link so that the application can use this. Again, this is pretty standard loader linker stuff. If we take a little bit of a closer look, we can see exactly what DYLD is doing. So when a new process is started, the first code that executes in user mode in that newly born process is DYLD_start. This is just a little assembly stub routine that then calls start and then main. Now this isn't the application's main, this is the loader's main. Main simply gets a path to the executable and calls link. Step 3, link calls recursive load libraries. Step 4 actually starts to parse the dependent dilibs and begins to call load library on each to start the loading process. Step 5, there's these various prerequisite functions that are called that do some parsing and some other analysis. And then finally in step 6, it calls load phase 6, which actually loads the dilib into memory and does all the linking. So that's a brief overview of DYLD. So let's talk about finding some logic that we can abuse to perform a dilib hijack attack. So basically we want to look for two scenarios. The first scenario we want to look for is there code within the loader that doesn't error out if a dilib is not found. And then the second scenario we want to look for is there code, again, within the loader that looks for dilibs in multiple locations. In either case, if the answer is yes, we may be able to hijack via a dilib hijack. Why? Well, think about the first scenario. If there's an instance where an application has a dependency and that dependency is not found, we may be able to plant a malicious dilib in that location and fulfill the dependency. Similarly, in the second scenario, if the loader is looking in multiple places for the dilibs to load, and the legitimate dilib is not in one of the primary locations it's loading, again, we may be able to plant or save a malicious dilib in that primary search location and then trick the loader into loading that. So let's start by looking for the first case, which is there a scenario which it's okay if a dilib is not found? So in the recursive load libraries function, we can see an exception is thrown if a dilib is not found. This is what you expect. If an application has a dependency and that dependency is unable to be fulfilled, the loader's kind of going to throw up its hands and crash. However, we can see in the catch statement that the exception is ignored if some variable that's named required is not set. And then there's an Apple comment that says weak libraries are okay. So we have to go to the doGetDependentLibraries method to see what sets this required variable. We can see some code that's iterating over various load commands, and we can see logic for the lc load dilib, which we talked about. And there's a new dilib, a new load command called lc load weak dilib. If the load command is this new lc load weak dilib, that required variable is set to false, which is good. That means the exception is going to be avoided. Pretty much it says if that dilib is not there, no harm done. So by abusing these weak dependencies, this is our first dilib hijack scenario. So here's a normal scenario. You have an application that has a weak dependency. The loader is going to go and try to find that dilib, but if that dilib is not there, the application's like, okay, I would have used it if it was there, but if it's not, no problem. So what a hacker can do is obviously plant a malicious dilib in that location, and now whenever that application is started, the loader will find the malicious dilib and be tricked into using it. Now that's the first method. I wanted to keep looking to see if I could find the second method, because the first one wasn't as common as I would have thought. So auditing the code, again, uncovered a loop. Basically, it was trying to load dilibs from multiple R-path locations. We can basically see there's an inner loop, which is a vector of paths, and it's trying each of these paths and seeing if it can find the dilib in each of these paths. So I had no idea what functionally this was doing, but luckily Apple explains. So there's two parts to these R-path, run-path dependent dilibs. The first is the actual dilib, which is called a run-path dependent dilib. A run-path dependent dilib is simply a library that doesn't know where it's going to end up on a target system when it's installed. The second piece are applications that link against these run-path dependent dilibs. Since the dilibs don't know where they're going to end up, the application has to have some knowledge so that it could tell the loader where to look. So this is exactly what happens. Now, I guess this makes it easier to deploy software, but from an attacker's point of view, we can see this and say, oh, DYLD is basically going to look for dilibs in multiple locations. This is promising. So I briefly want to walk through an example where we're going to build a run-path dependent library, and then we're going to create an example application that links against these libraries that then we'll use to hijack. So it's pretty easy to make a run-path dependent library. It's a normal dilib, except in the install directory, you put this special keyword that's @rpath. If you then compile this dilib and dump its load commands, you can see the lcid dilib, which again is the load command that tells or identifies the dilib to the loader. You can see that its name, which is a path, actually starts with this special keyword @rpath. Now, for an application to link or make use of such run path dependent dilibs, they got to do two things. So first, in Xcode, you just drag the local copy of your run path dependent library to create the dependency. And then you have to specify, you have to tell the loader where this dilib may end up on the target system when the software is deployed. So you do this by specifying some search paths in the run path search paths in Xcode. Again, when we compile the application, this is going to generate some load commands. First, there's going to be the standard lc load dilib load command because we have a dependency. But now there's these new load commands, which are the lc rpath load commands. And these contain the list of places that tell the loader where to look for the dilibs. So let's dump each of these load commands to show you exactly what I'm talking about. So this is first the lc load dilib load command. Again, this is in the application, and it simply specifies a dependency. It tells the loader, hey, I'm dependent on some dilib. Please go load that. Now, this is standard, except if you look at the name field, you can see that it starts with @rpath. Again, this tells DYLD, hey, as an application, I have this dependency. When I was built, I didn't know exactly where this dilib was going to end up on the file system, but I have some embedded search paths that I'd like you to go look for to find this dilib. So in order to find this dilib, the loader will then look for these lc rpath load commands. There's going to be one for each directory where the dilib may end up. So if we go back to the loader source code, we can actually see where these load commands are processed and how the loader interacts with them. So in the recursive load libraries method, we could see it calls this function called getRpaths. What this does is extract the run path search paths and puts them all into a vector. So it's going to get each of those search directories and just put them into an array into a vector. Now, it has a list of where to look. So back in load phase 3, which is one of those prerequisite loader functions, what it's going to do is it's going to look for all dependencies that start with that @rpath keyword. And then what it's going to do is it's going to swap out that @rpath keyword and put in one of the search directories, check if the dilib is there. If it is, it's happy. If not, it's going to iterate to the next search directory to look for the dilib there. So here's hijack number 2. Now, there's several prereqs, but it turns out they're pretty common. So we have an application that has a dependency on a run path dependent dilib. We can see the loader is first going to look in the applications library directory because that's the first lc rpath. Then after it doesn't find the dilib there, it's going to consult the second lc rpath load command and go there and look for the dilib there, which it then finds the legitimate dilib. So what an evil adversary, a malware, a local attacker can do is plant or place a malicious dilib in that primary run path search directory. And then every time the application is started, the loader will find that malicious dilib first, and because it's a first match wins, it will load that malicious dilib. It will be tricked into using our malicious one instead. All right, so to briefly summarize, I've described 2 ways to perform dilib hijacking on OS X. First, if an application has a weak dependency, that dependency is not there, we can plant a malicious dilib. Or if an application contains multiple run path search directories and the run path dependent library, the legitimate one, is not in one of the primary directories, again, we can plant a malicious dilib in the initial directory and it'll get loaded automatically. All right, so now it's time to actually perform hijack. We're going to use the example application we just built that has this dependency on these run path dependent dilibs. So the first thing we should do is confirm that it's actually vulnerable. So the loader has various environment variables that you can set that basically tell it to do more logging, tell you what exactly it's doing. So if we set the DYLD print rpaths environment variable, this will print all the information that the loader is trying to do as it tries to find these dilibs. So we can see on the slide, it first tried to look in the initial search directory and didn't find the dilib there. So then it went and looked in the second directory and it found the dilib there, so it's all happy. All right, so what we're going to try to do is simply build a dilib and drop it in that primary search directory. We'll cross our fingers and hopefully the loader picks it up. Now, one thing we're going to do is we're going to put an export constructor in our dilib. Now, the reason we do this is normally when dilibs are loaded, they're not executed right away. The application has to call into some export to trigger execution. But if you create a custom exporter, as soon as your dilib is loaded, it'll be automatically executed in a deterministic manner. So we plant our malicious dilib in the primary run path search directory. We start the application, and good news, bad news. Good news, the loader seems to have found it and tried to load it. Bad news, the app horribly crashes. Luckily, though, there's a pretty verbose error message that kind of says exactly what's going on. So we go look at the source code to see where this error message is thrown. Basically, we can see that within the recursive load libraries method, it's going to check that the version of the dilib that it's about to load matches the version that the application has a dependency on. This makes sense. If an application, say, has a dependency on a dilib and says, hey, I need at least version X, if the dilib that the loader loads is less than version X, the loader is going to crash and basically say, hey, I couldn't fulfill the dependency for you. Now, since we didn't specify a version in our hijacker dilib, it's going to be set to 0. And if we dump what the application wants, we can see it wants version 1.0. So we can fix this pretty easily. We just go back to Xcode, and there's actually fields where you set the version information. We recompile our dilib, and again, dump its load commands. We can now see the version is 1.0. So now we have a compatible version number. We take this newly compiled malicious dilib, again, copy it back to the primary run path search directory, execute the application again, crashes again. Different error message, though. It says, hey, you don't have the symbols I require. Again, this makes total sense. Applications have dependencies on dilibs because they want to use some functionality within the dilib. And the way this is all linked in and glued together is via symbols. In our hijacker dilib that we just copied in, we didn't export any symbols. So again, the loader is going to be like, GTFO, you don't have the symbols the application needs. So we got to figure out how to address the symbol issue. So we could manually create the symbols that the application needs, but this is problematic for two ways. One, it's a lot of work, and I'm kind of lazy. The other is that it's kind of brittle. We'd have to, say we're trying to hijack application A, we would have to export all the symbols for application A. If then we wanted to hijack application B, we would have to create a whole new set of symbols. So ideally, it would be way better if in our malicious hijacker dilib, we could just point to the legitimate dilib that we're hijacking and tell the loader, hey, I don't have the symbols that you need, but I know someone who does. And then as we hijack different applications, we could just update our malicious hijacker dilib to keep pointing to the correct legitimate dilib that we're hijacking. Turns out that in OS X, you can actually do this. There's some linker flags you basically pass. And this creates a new load command, the lc re-export dilib load command. Again, this tells the linker, I don't have the symbols, but this guy or girl, this other dilib has the correct symbols, so go get them from there. There's two issues, though, that both deal with LD, which is the compile time linker. The first is when you specify this export dependency, the compile time linker goes and gets the name of the legitimate dilib that you're re-exporting to. Since this is a run path dependent dilib, its name is going to start with this @rpath keyword. Now, this is only a problem because when the linker, the runtime linker, sees this lc re-export dilib load command, it doesn't actually resolve that @rpath keyword. It doesn't treat it as special. So it just tries to go to the file system and look for a dilib that starts with @rpath, which obviously is not going to exist. The other problem is LD, again, the compile time linker, will not allow you to link against or re-export to another dilib if that dilib is a system dilib under an umbrella framework, which a lot of the dilibs that we want to hijack are. So we can get around this by just linking against a fake dilib. This will allow us to compile, and then we can patch or fix up this lc re-export dilib load command so that it points to the correct dilib. Turns out there's an Apple tool to do this. It's the install name tool. And basically, you give it a few parameters. You give it the existing name or value in the lc re-export dilib load command. You give it the new value, which again, this is the full path to the legitimate dilib that we're hijacking, and then the path to our own hijacker dilib. And then when we run this, we can see in the slide, it's going to fully update the lc re-export dilib. So that it'll point to the correct dilib that we are hijacking, which contains all the symbols that the application needs. So we take this built hijacker dilib, copy it again back into the primary search directory, execute the application, and it finally works. Basically, our malicious dilib is automatically loaded and executed. All symbols are re-exported to the legitimate dilib so that the application runs and the user doesn't see anything fishy going on. All right, so now let's talk about some attacks and some defense. The attacks we're going to highlight, in my opinion, are pretty damaging and allow us to achieve all these cool hacks and malicious activities by simply planting a malicious dilib to the file system. That's all we're doing. We're not modifying anything else. Also, it's unlikely to be patched out because we're abusing legitimate functionality of the OS X loader. And it's also unlikely to be detected by security products because the problem is the loader is doing the one that's loading the malicious library. So that's, again, kind of, we're just abusing legitimate techniques, so that's hard for security products to detect and block. So first I want to talk about automation. So in order to do this dilib hijack attack, you have to have a vulnerable application. You can't indiscriminately just target any application. So I wrote a little script that basically scans the, either your running processes or all files on the file system and looks for applications that are vulnerable to either of the two hijack scenarios we described. And we can see that it found about 150 binaries on my box. So that's good. There's a lot of targets we can go after. Now, I can't list them all, but these are some of the ones, maybe some of the more well-known ones. We can see Apple has a whole list. Third-party applications like Microsoft have a whole bunch. This is a little funny because all their Office products were vulnerable to DLL hijacking on Windows. They're also vulnerable to DLL hijacking on OS X. And then a lot of third-party ones like Google, Adobe, PGB Tools, Dropbox. We can hijack any of these applications. Also recall, talking a little bit more about automation, that in order to successfully hijack an application, we had to craft a dylib that had the correct version number and also re-exported the symbols to the correct dylib that we were hijacking. And this was a kind of a pain to do manually. So again, I wrote a script that basically takes a generic hijacker dylib and configures it for the target you're about to hit. So for any application you're trying to hijack, you just run the script and it'll configure the hijacker dylib so it's fully compatible so that your hijack will work. All right, so I want to talk about persistence first. This is probably one of the best uses of attack. Again, our goal is to gain automatic and persistent code execution by simply dropping a dylib to disk. That's all we're going to do. The benefits of this, again, there's no binary or OS modification. So we're not breaking any digital signatures. We're not modifying anyplists or auto-run locations that might be monitored. There's also going to be no new processes. Our dylib, our malicious dylib, is going to get loaded into existing process. So the user's not going to see any new malicious processes running if they do a PS or check out activity monitor. Also, it's going to be hosted within a trusted process. This is good because a lot of times trusted processes are allowed to do more things than untrusted processes. And again, it abuses legitimate functionality. Anytime you have an attack that abuses a legitimate functionality, it means it's probably going to be harder to patch and detect. All right, so on my box, there is an application called the iCloud Photo Stream Agent. It's Apple daemon that gets automatically run whenever the operating system starts, so anytime I reboot my computer. And it turns out it's vulnerable to a dylib hijack attack. So what we can do is configure our malicious dylib so it's compatible with iCloud Photo Stream Agent's dylibs, copy it to the primary run path search directory, and now anytime the box is restarted, our malicious dylib will get loaded and executed automatically by the loader. So this is really stealthy persistence. We can also use dylib hijacking to gain persistent code execution within a process anytime it's starting. Now, there's a number of ways to do process injection. Normally, you have an external monitoring component that's waiting for your target process, for example, the user's browser. And then as soon as that browser comes up and you want to inject code into it, you allocate some memory, you copy in some shell code, you spawn a new thread. This works, but it's kind of noisy and a little bit complicated and easy to detect. Dylib hijacking can achieve the same kind of thing, code execution within a target process, without any of these downsides. So Xcode is an attractive target for malware because I think malware could use it to infect all deployed binaries, kind of as an autonomous propagation vector. So Xcode is the Apple IDE. It's what developers use to build applications. I thought it'd be really cool if there is malware that's running within the context of Xcode's process that's basically watching for a release build. And as soon as the developer builds that release build, the malware could either subvert the source code or actually at the compiler level inject some malicious code so that now the release binary is infected, and as it goes out, it'll propagate malware. So it turns out that Xcode is vulnerable to a dylib hijack attack. So again, we can customize, configure a malicious dylib, simply save it to the file system. That's all we have to do. Now, every time Xcode is started, our malicious dylib will get automatically loaded by the loader into Xcode's process space. If you can't trust the compiler, you should pretty much just go home. Another use of dylib hijacking is to bypass security products. Again, the goal here is we want to do something that normally would be blocked or disallowed. There are a lot of ways to maybe individually attack personal security products, but dylib hijacking provides kind of a nice generic way to bypass pretty much all of them. So let's talk specifically about Little Snitch. Little Snitch is the de facto firewall for OS X. I run it on my box, and what it does is anytime there's a new outgoing untrusted connection, it pops up and says, hey, do you want to trust this connection from process, XYZ? The problem or the approach that Little Snitch takes is it's kind of binary. It trusts known processes, and it also allows users to create blanket rules. So on my box, GPG Keychain is allowed to create any outgoing connection. This makes sense. GPG keychain is trusted, it's signed, it needs to talk to various key servers, update itself, so this rule makes sense. The problem is GPG keychain is vulnerable to a dilib hijack attack. So what this means is we can plant a malicious dilib, and then every time GPG keychain is started, either programmatically in the background by an attacker or by the user, the malicious dilib will get automatically loaded and execute and now be in the trusted process context of GPG keychain. And then the malicious dilib can create an outgoing connection to any network endpoint at once. It's command and control server, anywhere else. A little snitch will see this, but it says, hey, this is GPG keychain. I trust GPG keychain. I'm going to let the connection out. So this is, again, how we can use dilib hijacking to bypass security products. Now, so far, we've talked about local attacks, and these are great for persistent malware. But I wanted to take this a little bit farther. I want to be able to infect remote users. But there is this built-in security component of OS X called Gatekeeper that keeps getting in the way. This is something we want to bypass. So how does Gatekeeper work? Basically, every time you download content from the internet, this content gets tagged with a quarantine attribute. And then when you go to run that application, so you double-click it on your desktop, Gatekeeper will first intercept this request the first time and make sure that the application you're about to run conforms to the system settings. So you can see on the slide, you can set Gatekeeper to various settings, the highest being only allow code from the Mac App Store. This means if you download code from anywhere else and try to run it, Gatekeeper will pop up and block. Gatekeeper actually does a decent job blocking malicious downloads. A lot of times users are faked into downloading some Flash update or something. It's really not a Flash update. So Gatekeeper will block this if it's unsigned. Also, if there are man-in-the-middle attacks that are being performed against software, Gatekeeper can detect and block this because the digital signature will obviously have been modified. So Gatekeeper does a great job verifying the downloaded application, but it only verifies that. External content was not verified, which is okay, except if the application loads that external content. So this is what we're going to do in 3 steps. I guess we only need 2. First, we're going to find an Apple-signed or Mac App Store-approved application that contains an external relative reference to a hijackable dilib. We're then going to create the necessary zip package, DMG package installer, or inject into a legitimate dilib, and build the folder structure necessary to execute this. So let's talk about these steps one by one. So first, we need to find a Gatekeeper-approved application with an external relative reference to a hijackable dilib. It's got to be external because we can't modify the application bundle. Gatekeeper is verifying that. If you touch that at all, it's going to break it, and Gatekeeper will not allow it to execute. However, the content has to be externally relative because we want to be able to put it within the same zip file, within the same DMG image. So instruments.app fits the bill. We can see that it is verifiable, accepted by Gatekeeper. It's an Apple-signed binary, so Gatekeeper's like, even if you download it from the internet and I have only allow from the Mac App Store, I will allow you to run this application. And if we dump its load commands, we can see it has an LCR path that's relative externally to the application bundle. This is because Instrument expects to be installed under xcode.application. So at runtime, it kind of goes up into Xcode's shared framework directory and looks for shared dilibs there. But we can abuse this. So now let's create a DMG image. We could also create a zip file or inject this into a legitimate download if it's over HTTP. So at the top, you can see there's instruments.app. It's under the applications directory. And then there's the external folders that instruments.app will look for dilibs to load. Now, if we provide the user with this DMG image, they're going to be like, what is this? Where do I click? I mean, I'm not going to run this. So we can take some steps to clean this all up. We can hide these files and folders. We can set a top-level alias that points directly to instruments.app. We can change the icon. We can change the background. Again, we can modify all of this because we're not modifying the digital signature of instruments.app itself. So, if you're downloading a Flash installer, a legit Flash installer over HTTP, and this is what you get, you're probably going to run it. All right, so this is how this all happens. So again, we have max Gatekeeper settings. We say only allow code from the Mac App Store. And then we have this malicious DMG that has our unsigned malicious dilib, which should not be able to execute because it's not from the Mac App Store, and then instruments.app. So when the user clicks it, they'll get a standard pop-up. This is the standard Gatekeeper pop-up you get for any content you download from the internet. Even if it's signed, validated, you're just going to be like, this is from the internet. The user is probably going to click OK because they've just downloaded some software that they want to run. And if they do, even though Gatekeeper is set to only allow code from the Mac App Store, it will actually load our malicious unsigned dilib because it doesn't check for that. Apple actually patched this, so we're safe now. Gave me my first CVE, which I'm kind of stoked about. But this was problematic until they patched it because this allowed hackers to kind of go back to their old tricks and get users to download malicious software and infect themselves. So the way most hackers, non-nation state people target Mac users is by getting people to download malicious software. So you go to a website, it tells you there's some HD codec you got to install. You have to download some Flash installer, stuff like that. Or you go to Pirate Bay and you want a free copy of Photoshop. Hackers would put malicious code in there and infect the users in that way. Gatekeeper would block this because those were unsigned, malicious binaries. But now using this attack, hackers could go back to their same techniques and infect Mac users. Now, hopefully we're all security conscious professionals here, so we're unlikely to be downloading shady content, hopefully. However, we do all download software. And since the Mac App Store is so constrictive, a lot of us go get the software from the company's website. So if you want to download Photoshop, you probably go to adobe.com, Microsoft Word, you go to microsoft.com. And this is problematic if this software is distributed over HTTP, because what this means is now a nation-state adversary or an adversary that has network-level access can inject malicious code into these downloads, and Gatekeeper will no longer detect that they have been tampered with. Now you might be thinking, it's 2015, how much software is really distributed over HTTP? So when I was doing this research earlier this year, I looked at my dock, and about 2/3 of the software that I had installed on my computer had been distributed to me over HTTP. Now you might be thinking, all right, Patrick, you are a malware analyst, security guy. You're probably downloading a lot of random tools from random third-party sites. Not too surprising that it's over HTTP. So I said, all right, fair enough. Let me look at security tools, firewalls, antivirus products. These guys are supposed to be the shining example of how to do things right. Well, it turns out, again, when I did this research earlier this year, every single third-party security product that I downloaded was downloaded over HTTP. So again, this means any network-level adversary could have easily intercepted this download, injected malicious content, and now Gatekeeper would not flag that the binary had been modified. Kind of unfortunate. So I wanted to put everything together to kind of test these third-party security products. So I built a proof-of-concept piece of malicious code that was distributed as a malicious DMG or zip file, or it could be injected to a legitimate download if it was over HTTP. When executed, it would persist via a DLL hijack. It would then exfiltrate some data to a command and control server on iDrive, and then download and execute some commands. Again, this isn't the most sophisticated piece of malware, but I think it represents well what most malware today tries to do. Persist, exfil, download, and execute. Also, you don't need root to install this. So then I wanted to test this against these third-party security tools. And the test I thought was simple but realistic. Would download the security product over HTTP, update it so it had the latest signatures, and then I would run my downloaded.dmg image to see if the antivirus product or the firewall detected the attack. And I skewed the test towards the third-party security products by saying if they detected any component of the attack, that was a win for the antivirus product or the firewall, a loss for the malware. So if they detected the Gatekeeper bypass, they detected the persistence, they detected the exfiltration of data, the download, the execute of commands, any of those detections would be a win for the antivirus company. Now, probably not too surprising to you guys, none of them detected any of this. So again, this really just kind of re-exposes in my opinion, the ineptitude of an entire industry that unfortunately charges us for their products. All right, so pretty much things are kind of broken. So I wanted to briefly talk about some suggested fixes. First, since DLL hijacking is legitimate, it's unlikely to be patched. So I don't really know how to protect against this. Gatekeeper, I reported this to Apple. They patched this, which was great. But the way Apple patches things is very narrow-minded. So if there's a vulnerable piece of code, they'll generally just patch like the code path to that vulnerable code. So I'm giving a talk actually tomorrow about a priv escalation and Apple's patch and how I was able to bypass the patch. Again, with this Gatekeeper patch, there's other avenues to still coerce Gatekeeper to run unsigned code. I demonstrated this at Black Hat a few days ago, even on El Capitan. So hopefully, I've talked to Apple about this. Hopefully they fix this as well. So it's improving slowly. And then also, if software is downloaded over HTTP, let the company know. Like, write them. Be like, why are you distributing software to me over HTTP? It's 2015, right? Get your act together. So I briefly want to talk about OS X El Capitan. I was hoping that DLL hijacking would be addressed. Unfortunately, though, even though there's all these new security mitigations, well, at least according to Apple marketing, DLL hijacking is alive and well. So what I did was I scanned the system, I found some vulnerable applications, and I was able to plant a malicious unsigned dilib, and now every time the operating system was started, the malicious dilib was still loaded. Apple specifically says that code injection into system binaries is no longer permitted. But using dilib hijacking, we can still get malicious unsigned code into vulnerable system applications. So I don't know. I don't know if they'll fix this, but I guess that is what it is. So it looks like this attack, unfortunately, will be around for a while. So I decided to release a tool that can at least help us locally. So DHS, dilib hijack scanner, basically will scan your running processes or your entire file system, and it'll tell you two things. It'll tell you if there's any vulnerable applications. Now, there's probably going to be a lot of vulnerable applications. This doesn't mean you're hacked or hijacked. This means if malware were to infect your system, it could plant a malicious dilib and only have to do that, and then it could get code execution or get that dilib loaded automatically by the operating system. It'll also show you hijacked applications. These are applications that appear to be hijacked. Now, there's some false positives, so if you find this, don't freak out too much. I've yet to see any malware abusing this technique. But this will detect all the attacks I talked earlier, where if someone does plant a malicious dilib to hijack a legitimate one, this tool will detect that and show you. This tool is available for free at objectivec.com. That's my free personal OS X security website. There's a nice collection of Mac malware if you guys want to download and play with some recent samples. I find it's kind of hard to get the AD companies to share malware with me. So I spent a lot of time kind of getting this collection together so you can download. There's also some free tools that I run on my personal computer. I love my Mac, but in my opinion, it's really easy to hack. So I kind of basically just wanted to write some tools to protect it and then make them available for free. So the first tool is Knock Knock. This is simply auto runs for OS X. It'll show you all software that's automatically persisting. Task Explorer is pretty much like Process Explorer, the sysinternal tools for Windows. Shows you all the running tasks. If they're signed, it has virus total integration, allows you to see loaded dilibs, so it would show any of these injected or hijacked dilibs, network connections, open files. And then finally, BlockBlock. BlockBlock is simply a firewall for persistent auto-run locations. So it'll monitor the file system, and if malware tries to persist or install itself, it'll detect this. All right, so wrapping this all up. So we've talked about a relatively new class of attack that affects OS X. Pretty much affects everyone. It affects Apple applications. It infects third-party utilities. And it abuses legitimate functionality and is fairly stealthy. And using this attack, we can do all sorts of cool things. We can persist really stealthily. We can gain low-time process injection, even on El Capitan. We can bypass security products, and we can also facilitate remote infections. So until Apple fixes this, which they may or may not, I would recommend scanning your system, make sure you're not hijacked. Really doubt that you are, but can't hurt. Also, only download software over HTTPS. And if you see a company distributing software over HTTP, send them a little nasty email or something. And then, this is my personal opinion, I don't think the antivirus products are worth paying any money for. They cost money and they don't really detect anything. All right, so that's a wrap. We have 2 minutes for Q&A. You can find me on Twitter, email, slides available for download. I wrote a white paper about this technique for Virus Bulletin, so if you want to read all the excruciating technical details. And check out objectivec.com for free security tools. And also check out synac.com. We're an awesome company. So that's it. Are there any questions? Yes. Some of the UI ones not, but there are open source versions of Knock Knock and the dilib hijack scanner. Those are on Synac's GitHub repository, so you can download and play with those as well. Yes. Any other questions? Thank you. Gentleman in blue. Okay, yeah, the question is, how does this impact iOS? So I believe the code is kind of vulnerable because they share a lot of the same loader code, but because iOS does not allow you to run any unsigned code, that right there kind of blocks all this attack. It only runs Apple signed code. So even if an application was vulnerable and you planted a malicious dilib, the loader would just ignore it because it's not signed by Apple. Any other questions? Yes? That's a great question. So I think one thing, the question was, could you require the dilibs to be signed or something? So Apple, I think, should say, if I'm an Apple sign process, I should only be loading Apple signed binaries. Or if I'm a sign process, I should be only loading signed dilibs. So yeah, one problem that you could generically prevent this is say, don't allow unsigned libraries, unsigned dilibs to be loaded in that. Now, it's not that hard to get a developer ID and then get Apple to sign it, but it would make the bar a little higher and generically I think would prevent a lot of the attacks. So, great question. All right, I think I'm about to get kicked off the stage. Thank you again. I will be hanging out here. So if you have any questions, I would love to chat.